All right, guys, this is Unit 3, Video 1. This is the second lecture of the unit, the first one we did in class. All right, so this lesson is going to talk about Newton's second and third laws. Remember last class we talked about Newton's first law of inertia, and we're going to talk about action-reaction pairs as being the same type of force, and we're going to solve some word problems involving force, okay? This first thing I want you to do is I want you to recall the first law that describes inertia. And I want you to think about this problem, and then we are going to do the demo in class, but I want you to write down your guess as to what will happen. So this question asks, which string will break first if I pull quickly, and what about slowly? So you can see there's a string, and then like a little mass, and then another string. So if we pull it really fast, which string do you think will break, top or bottom? And then if we pull it really slowly, which string do you think would break, top or bottom? We're going to do this in class, so just take a second and write down your guess. So pause the video, write down your guess, and then when you're ready, come back. All right, Newton's second law. Pretty simple. Newton's second law is just an equation. But basically what it says is to change the motion of an object, you must apply a force. You could also say to accelerate an object, you must apply a force. So the equation is this, and it's one of the more famous physics equations that most people kind of know, or at least have seen. Okay, so force equals mass times acceleration. Let's go ahead and just put those words in so you know what these are. Okay, and the units for force are newtons, named after Isaac Newton, and so we have to use a capital N because it's a person's name. Okay. All right, let's go down here to the bottom. Okay, so a force is any push or pull. Okay, any push or pull. Let me move this out for me. There are two main categories of forces. Okay, we have a contact force or a field force. They're pretty much what they sound like. A contact force means that two objects are touching in order to create that force. Okay, there has to be some sort of contact between the two objects. Examples of this would be friction, the normal force, you pushing on a crate, you pulling on a suitcase, any of those things. A field force is sort of weird. It's sort of like in a movie when you think about like, they say you have like a field force around you. Basically what it is a field force is a force that doesn't need contact to act on an object. So the best example that I think you guys can think of it would be like gravity, right? Gravity doesn't touch you, but it pulls you in a certain direction, pulls you downward. The other example would be a magnetic force. The other one would be an electric force. We will not deal with magnetic forces, and we won't deal with electric forces until the last unit of the year. So really you're only worried about gravity as the only field force that we know and are going to worry about for now. Okay. The force of friction. Okay, this is a contact force, and it's what happens when two objects slide past one another. Okay. It's basically that rubbing. I think you probably have heard about friction before. And we're going to dive deeper into these different forces in future lectures, but this is just kind of giving you an idea of what these are. We use FF to represent friction. Okay, so F is for force, little f is for friction. Okay. Force of gravity, we use F little g or W. And the reason that we have those two, we have W, is because the force of gravity is also the weight of an object. So the reason that you have weight is because gravity pulls you downward. If you were on the moon, you would have less weight because gravity is less strong on the moon. okay? And we're just going to say it's a pull for now we're going to worry about Earth, okay? But Earth, Moon, other planet, doesn't matter, okay? All right, and then what I want to specify here too is that your weight, and we will go over this again, but your weight or your force of gravity is equal to your mass times the acceleration of gravity, which would be that negative 9.8. That's the acceleration of gravity. The force of gravity would be your mass times that, right, because of this equation. So the force of gravity would be your mass times the acceleration of gravity. Okay. All right, the normal force, and I will demonstrate this force when we get to class, but the normal force is a surface force. And basically what this force is it's what keeps objects from falling through other things. So right now my computer is sitting on my desk, so there's a force pushing the computer up, right? Gravity's pulling the computer down, and the desk is pushing the computer back up so that it doesn't fall through the desk. If you're sitting in a chair, then the normal force is the chair pushing up on you so that you don't fall through the chair, okay? We use, I think we use big N, but I'm just going to use Fn for now. Let's just use that instead. Your book might use N, but it gets confusing with newtons. So let's just use Fn. And the really important thing to note is that the normal force always works perpendicular to the surface. So if it's a table with a book on it, the normal force is going to push up, right? If it's a ramp with a car on it, the normal force pushes perpendicular to the ramp, okay? If it's a wall and you're pushing something up against the wall, right? So let's say that book is up against the wall is going to push this way, okay? All right, and then tension, we use big T, okay? And tension is the force on a rope or string or cable. Okay, so it's just a force that's being pulled through a rope, string, or cable. If it's one rope, the force is the same, the tension is the same throughout the entire rope. You can't have one side be really tight and one side be really loose at the same time if it's the same rope. Okay? All right, let's go to the next page here. All right, Newton's third law. Okay, Newton's third law is probably something you've heard before, but it's for every action there is an equal and opposite reaction. Okay, it follows three very, very important rules. Okay, the forces are the same type. So if gravity pulls down on an object, then that object pulls, that's kind of a bad example, up on gravity. That doesn't make a lot of sense to you right now. Let me think. If you pull on a rope, like you're playing tug-of-war, then the rope is pulling back on you with a tension force. So you pull on the rope with a tension force, the rope pulls back on you with a tension force. Okay, so same type of force. That won't really be as confusing as I'm making it sound right now. This is the one that is most important. Well, both of these are very important. Okay, it's exerted on two objects at the same time. Okay, so if I pull on a rope and you pull on a rope, the opposite and equal forces, this reaction-action pair, is not me pulling on the rope and you pulling on the rope. It's me pulling on the rope and the rope pulling on me. So those two different objects, not us both pulling on the same rope. Okay, and the forces are equal and opposite in direction. Okay, always. A couple examples. The action, these are called action-reaction pairs. Okay. And a couple examples here. So the tires on a car push on the road, right? So when you drive, the tires push back on the road. The reaction is that the road pushes on the tires, which is how you move forward. Other example, while swimming, you push water backward. The water pushes you forward. That's how we swim. We know this rule already. We use it all the time. We just haven't really put it into words yet. Okay. And then I want you to take a moment, pause the video, think of a few on your own, and write them down here. Yes, I am going to check when I check your notes that you wrote some down. So write at least 2 examples down. Okay, last thing that I want to show you, and in class we will watch a little Mythbusters, which will be fun. But the last thing I want to show you is this third law that we just talked about is the reason that we have the ability to get rockets into space and to have rockets move while they're in space. Okay, this was probably the most commonly missed conceptual question of every single test last year. Okay, the way that a rocket works, okay, and the way that it moves is by putting a force, pushing the fuel back, or whatever, and then the fuel pushing the rocket forward. So the rocket pushes the fuel one direction. Okay, so rocket pushes fuel in one direction, and the fuel pushes the rocket in the other. Okay. Most common answer was rocket pushes on ground, ground pushes on rocket. That's a great answer until it doesn't hold up when you're actually in space and there's no ground. Okay, so be careful here. The ground has nothing to do with it. The rocket pushes the fuel pushes the rocket. That's the right answer. Okay, and it's right here starred like 45 times because it's important. Okay, we will watch Mythbusters in class and talk a little bit more about the rocket and these 2 laws. All right, you're done.